All right, let's just dive right in. We are taking on a massive, mind-bending challenge today in this explainer. We're talking about mapping the math of a holographic universe onto our actual, real-world flat reality. It's a journey into theoretical physics where, honestly, the rules are literally still being written as we speak.
And because those rules are still unwritten, we find ourselves in what one prominent physicist just recently called a, quote, kind of wild west of flat space holography and ideas. No kidding. The frontier of theoretical physics right now, it is completely untamed territory, and today, we're the ones exploring that exact landscape together.
To help us navigate all this, here is our quick roadmap for today. First, we'll cover the holographic universe. Second, the flat space problem. Third, squishing the light cone. Fourth, the swing surface. And finally, number 5, the new holographic dictionary.
Okay, part 1. The holographic universe. Establishing the baseline. So just as a super quick refresher on ADS/CFT, you know that a 3D volume of space, which physicists call the bulk, can actually sometimes be perfectly described by a lower dimensional boundary, specifically a 2D conformal field theory. Basically, that outer boundary contains all the information of the entire interior. It's like a giant cosmic hologram.
Which brings us to entanglement entropy. By using the Ryu-Takayanagi, or RT formula, we can measure the quantum entanglement happening in that 2D boundary theory. And here's the wild part. It corresponds perfectly to the physical area of a minimal extremal surface deep inside that 3D bulk geometry. So it literally forms a direct bridge connecting the quantum information on the outside with physical geometric shapes on the inside. How cool is that?
Moving on to Section 2, the flat space problem, leaving the soup can.
All right, here's where things get tricky. Anti-de Sitter space, or ADS space, is usually visualized mathematically as a solid cylinder. Think of it like a soup can, where the holographic boundary is just the tin surface on the outside. But our actual universe, which is modeled as Minkowski space, well, it's flat. So, as you can probably guess, trying to force those elegant mathematical models from a theoretical soup can into the sprawling flat space of our actual universe, yeah, that creates some massive friction.
When physicists try flattening out the universe's math, they immediately slam into 3 huge roadblocks. First, the mathematical scale of that ADS space just completely diverges. It has to be sent out to infinity. Second, that nice, tidy boundary where our hologram was living gets pushed infinitely far away to something called null infinity. And third, the geometric geodesics that actually try to reach that boundary, they're forced to travel at the exact speed of light, which makes them null. Long story short, the normal holographic rules simply stop working.
Let's jump into Section 3, squishing the light cone, the mathematical limits.
To fix all this broken math, we have to look at how space and time can be stretched and, well, squished. If you take the ultra-relativistic Coriolis limit, a standard light cone gets squished completely sideways. This effectively drops the speed of light on our holographic boundary all the way down to 0. Now contrast that with the non-relativistic Galilean limit, where the light cones just squish straight down. To make the physics of our boundary actually match up, researchers lean heavily into that sideways Coriolis squish.
Now, as we push that speed of light to 0, the classical symmetries of the universe don't just break, they actually evolve. The standard Virasoro symmetry we had from the soup can model smoothly contracts into something way richer, an infinite-dimensional mathematical structure called the BMS algebra. It's a structure that is perfectly suited to accommodate our flat universe.
That takes us to Section 4, the swing surface, a new geometric shape.
Remember that standard Ryu-Takayanagi formula we talked about earlier? Well, since it completely shatters when we move into flat space, researchers really had to adapt. Enter the Bacci-Grumler proposal. This provides a completely new mathematical formula to calculate entanglement entropy, specifically tailored for this infinite-dimensional BMS field theory out there on null infinity.
But what does that new math actually look like physically? Well, researchers discovered a physical bulk shape built through 3 very precise steps. Step 1, you pick a specific interval way out on that boundary at null infinity. Step 2, you shoot radial light rays, or null geodesics, inward from the edges of that interval. And finally, step 3, you suspend a minimal extremal curve right between them. The resulting shape literally looks like a swing hanging in the middle of space, which is exactly why they call it the swing surface.
All right, our final section, number 5, the new holographic dictionary, reproducing the physics.
So now that we have this geometric swing, we desperately need a reliable dictionary to translate the physics back and forth between the boundary and the bulk. And researchers found that they could perfectly match these complex flat space functions by spearing or, smearing theoretical operators along those radial bulk light rays. Doing this miraculously reproduces the exact correlation functions for those BMS symmetries. It's a real game changer.
But to ensure those two-point functions work flawlessly without breaking the fundamental rules of physics, researchers had to borrow a really clever cheat trick directly from celestial holography. By using something called analytic continuation to the principal series, they can effectively save the calculations, mapping everything out seamlessly between the bulk and the boundary.
Looking out over this Wild West frontier, researchers are currently applying this exact framework to tackle some massive upcoming challenges. We're talking about using quantum entanglement as an actual resource for scattering experiments, decoding flat space mutual information, and defining completely new geometric probes that naturally live in flat space. This right here, this is the toolkit that is going to help us finally decode the actual flat space that we all live in.
Which brings us to the ultimate puzzle at the very edge of this frontier. How does quantum entanglement ultimately power scattering in our universe? It's a profound, wide-open question, and it really proves just how much remains totally undiscovered in the untamed flat limit of our reality.